All right. Let's begin. Let's begin the lecture. So today, what I want us to study is in terms of regular mechanics. I would call it forward dynamics. Okay. So I will explain exactly what it is, but it is a familiar term for you as a robotics student. You remember forward kinematics, inverse kinematics. You probably remember forward dynamics, inverse dynamics, right? So today, forward dynamics. But in a way, here, what I will focus on is not even forward dynamics so much as projectors. This is very related to forward dynamics, as you will see. In a way, here, when you listen to this like first slide, you can ask me, how is the forward dynamics a separate topic? Because last lecture, you remember, what we finished with was analytic solution to mechanical equations. So we described mechanical equations. We saw how mechanical equations with constraints work. And we even found analytical solution for them, right? Even on the first lecture, I showed you something like analytical solution to general case equations with constraints, differential algebraic equations, when you could differentiate constraint equation to get expressions for algebraic variables and higher order derivatives, right? So in a sense, forward dynamics sounds like it should be not a topic like we already covered. But you'll see this lecture, the important mathematics, which underlie, significant portion, I could say, of literature on systems with constraints. So what I'm going to show you here is, in many ways, a theoretical foundation for a big number of papers that deal with these types of systems. So while it sounds to you like we already know everything about it, what I'm going to show you here is going to be like crucial if you're going to study all the papers that people publish on this topic. So in a way, this is this discussion is one of the more important parts of the course, especially if you are seeing yourself as a practicing scientist in the area. All right. But I think as we go, I will convince you that this is more than, the topic is more than just solving the equations. All right. So with that in mind, let's go. So first, before we begin, let me quickly show you again the differential algebra equations for manipulator. So here they are. This is the manipulator algebraic differential equations. Let me remind you again quickly what those terms are. This is generalized inertia matrix, right? This is constraint Jacobian. You remember that this guy is multiplied by this guy. And this is kind of like reaction forces from Cartesian space mapped to generalized forces produced by those Cartesian forces, okay? Same with torques, right? And this is the right-hand side of this manipulated equations. When we put Coriolis forces, gravitational forces to the right-hand side, right? Those are external generalized torques. So motor torques will be here in this tau. Okay. This is constraint equation. So this is this says that constraint Jacobian times second derivative of generalized coordinates, so times accelerations, is equal to minus, Jacobian derivative times q dot. Where this came from, you remember this was a second twice differentiated constraint equation. Okay. All right. Now this has a solution if there exists a sure complement of this form. Okay. Sure complement of this form. What this is, you can kind of see it here, is inverse of this matrix multiplied by this on the left and on this on the right. Yeah. There is also minus sign in front of it and plus plus this element. So full form would be 0 minus J transpose H inverse J. But this is 0, so we have a simpler Schur complement here. And it should be full rank, because in the expression for analytical solution to this equation, this Schur complement will be inverted. Okay, so it has to be full rank for the solution to exist. All right. Now, we have this analytical expression here that describes solution to this equation. So equation is here, solution is here. Let's look at it a little bit. I'm not going to spend too much time on it right now, just a little bit. Okay. So here we have H inverse minus this matrix where you have H inverse on both sides. Okay, H inverse on both sides. Here you have J transpose J. So this is like a conjugation, you can see. And here you have a HG, which is inverse of the Schur complement. Okay, so H sub G is inverse of the Schur complement. That's my notation. You know, I don't want the slides to be too crowded, so that's why I introduced it. Okay. So Schur complement inverse appears here. Okay. This element basically is a coefficient of proportionality between this right-hand side of manipulator equations and generalized accelerations that they are producing. So apparently right-hand side of manipulator equations will be multiplied by this huge thing, like a inverse of Schur complement, which is conjugated by constraint Jacobian, multiplying both sides by H inverse. And this is like minus H inverse. So this is an analytic formula. You can try to derive it yourself. It's not impossible. You know, you can do it. Just as we do it in school, right? You express something from one equation, substitute into another equation, express it out, and then you get all of this. Okay. Now, those two terms are much simpler, and they are also similar to each other. They can appear as a transpose of one another. Appear. They're not, yeah, they appear as a transpose of one another. Okay, that's, I think, a sufficient term. They appear as a transpose of one another. Here you can see H inverse, right? H inverse. Here you see again Jacobian transposed, and you have inverse of Schur complement. Here the same thing, but you have a minus sign, and you have Schur inverse Jacobian. Notice not transposed, and you have H inverse. H is invertible matrix. Okay, so H is invertible matrix. Sorry, invertible. It's not only invertible; it's also symmetric. Since it is a matrix of a quadratic form. So H inverse is also symmetric. So H inverse, H transpose is equal to H inverse transpose is equal to H inverse. Sure, this guy, like in this form, is also symmetric, because you see that this, like, this matrix is symmetric. This type of multiplication would also leave it symmetric, and inverse preserves symmetricity for full rank matrix, unless I'm missing something. But yeah, it is symmetric. Yes, some questions? Okay. Okay. So yeah, and here we have again Schur complement inverse. So this is not a formula that you have to memorize or anything. You can derive it always. You know, I have personally find it very useful. Like, there are plenty of resources you can use. You can go to Wikipedia page and look up how they derive it. Of course, you know, you can also look at any textbook anything like that. Yeah, the expression for analytic expression for the block inverse is available. It's not very difficult to use. So that's where you can get to follow this from. Okay, and also what I want to, while we are here, what I want to point is this is not like nonsense. As in, when you look at it, it kind of looks like a mess. It's not such a mess. It's, you see, it has like some properties. Looks, very symmetric. There is a minus sign, so it's not symmetric. As in, like, if you transpose it, you would get not get the same, the same expression, right? The minus will travel, but it looks quite symmetric, right? There is this symmetry of what do you call them? Shore complements here and here. You have this insistence on multiplying both sides and so on. So it's like, it's not chaos. It's a reasonably beautiful mathematical expression. And what's also interesting is that it's not difficult to derive it, right? So it's quite easy. So you shouldn't try to run away from it. It's very typical to see people trying to avoid long algebraic expressions, but this particular one, there is no reason to avoid it. So when you work with those systems, always keep in mind that this is an option to rederive this kind of stuff for a different equation or something. So this is normal. There's nothing difficult about it. Do you have questions? I think, like, I feel like someone wants to ask them. Yeah, if you want to ask something, just talk over me. Like, don't wait for me to pause, because I will speak like non-stop. So just start speaking. I will stop. I will pause, and you can ask your question like anytime. Just interrupt me. I will remember where I left, so don't worry. Okay. All right. Now, this is, this is it. You would think, okay, this is forward kinematics. Now, for sure, we know what forward kinematics is, right? Forward kinematics is just to get this, you multiply this by this, and then this by this, right? That's forward kinematics. Okay, fair enough. Right? Now, explicitly, this looks like this, right? Again, what I said, right? This expression multiplied by right hand side, this expression multiplied by j dot q dot. Okay, and we have what's also interesting, we have a separate solution for reaction forces, which looks like this. Okay. Yeah. Remember last time we said that Schur complement should be a full rank, and for that we said that constraint Jacobian should be full row rank if we're talking about this guy. This guy should be full row rank. Or if we're talking about this guy, it should be a full column rank. So the constraints should be linearly independent, which implies that as rows of J or columns of J transposed should be linearly independent. Okay, and we said that there could be tricks of rewriting constraints, so we get different reaction forces, but the equations will become full rank. So keep it in mind. Like all of this, those analytical solutions can assume that that this guy exists because there's an inverse of Schur complement and there are conditions associated with it. Okay, fine. So now we have mathematics to just compute, if you want, this reaction force. Oh, sorry, reaction forces and second order derivatives. Okay, good. Important again to keep in mind that it is possible to compute those things, right? Just like that. Okay. Now we can do some manipulations with this kind of stuff. So let me show you one manipulation that we can do. So first, we can substitute expression for lambda back into the original equation, which looks like this. Okay. So let me emphasize. So the equation, manipulator equation, looks like this, where h is this right-hand side. Okay. I put the minus sign here. I have reasons for that, just for beauty of subsequent equations. But yeah, so this is the right-hand side of, you can say this is left-hand side, or my right-hand side is a minus sign of the manipulated equations. So now we have expression with, one unknown, another unknown, and the right-hand side as a single variable. So that's the idea. Okay, now what we do is we take lambda, expression for lambda from the previous slide, and we substitute it here. Okay. Now with that, what we can do is we achieve, same HQ double dot, here, HQ double dot. We have this J transpose, this J transpose. Now, instead of lambda, what we have is this whole thing, okay? Or to be more precise, what we have is this is a lambda now, okay? This is lambda. This is still the same J transpose, okay? Same J transpose. All right, and you have the right-hand side. Oopsies. Okay. So substituting lambda, we get all of that. All right. The expressions for lambda, you remember, looks like, minus h sub j, j h inverse, right-hand side, minus h sub j, and this j dot q dot. See, h sub j, j h inverse, right-hand side, h sub j, j dot q dot. Okay. So just substitution. Now, next step is we want to collect some terms. So what do you mean? Well, first of all, we have this guy here on the right-hand side and here. What we would prefer is to keep it all on the left-hand side. So on the left-hand side, yeah, in here. So if we transfer it to the left-hand side, we'll get 0 on the right-hand side. And here we would have this additional I, right? Because we have, let me emphasize, we have this guy. And we have identity in front of this guy. So now we have identity and this. And this minus here, like this particular minus here becomes this minus, okay? So that's what we do. So essentially, we simply collected the terms in front of H. Good. If we put that all, yeah, we could have collected them on any side. All right. So we have this expression, which is I minus all of this. Good. Now, what I propose is to consider a different equation. Like, this is nice. We will keep it in mind. But let us now consider a different equation. Different equation looks like this. I minus J transpose H sub J, J, H inverse, times what looks like a manipulator equation. Okay, this is manipulator equation, unconstrained manipulator equation. Because remember, here is what H is, right? And here is like a big H kilobodot. So this equation in orange here is HQ dot plus CQ dot plus G minus tau. This is just a manipulator equation in the form where right-hand side is 0. So this is just manipulator equation, but without constraints. Okay. Good. Times this red expression. This red expression is this expression. Notice it is the same thing, right? I minus J transposed H sub J, J, H inverse. Okay, so the same exact expression, but now multiplying the manipulated equation. Okay, now let me do some manipulation with it. first, I open these brackets. So I times HQ double dot is HQ double dot, right? Okay. Let me even be more careful. What the brackets that I want to open are actually, let me be very, very careful. Actually, these brackets. Yes, sorry. I open these brackets. So this brackets I open. Not these brackets, because there are two sets, right? I open these brackets, the right ones. So that's what I have. Okay. Next, I would have this expression. Let me again double check. You have this expression times this guy, right? So before we have I times this guy, and we get this guy. Now we have this orange expression times, again, the same guy. And what we have is here. What happened is that this and this cancel, like H inverse and H cancel each other. So we have, G, all of this, right? G transpose, H sub J, J times Q double dot, because H inverse and H cancel. Okay. Probably clear enough. All right. Next, what we have is this. Let me get this small h in front of this whole bracket. So this bracket, I just don't open it for h. This whole bracket I keep it. All right. So this expression we get. Notice this is just opening the brackets. Next, I remember one interesting fact. And that fact is that we have constraint equation, right? Constraint equation looks like this. Jq double dot equals to minus j dot q dot. And we have here, as you'll notice, jq double dot, right? So we can replace it with minus j dot q dot, right? And we have a minus sign here, so it will go away. So what we will have is the same expression, but now it will be j transpose h sub j, j dot q dot, right? Yeah, very, very interesting. But we can do it because it is part of the equation. Now, what we achieved is this, and everything else remains the same, right? Everything else remains the same. So just to double check, this remains the same. This remains the same. Okay. So nothing else changed. Now, notice that not only that remains the same, but also this equation is exactly the same as the equation above. Okay, term by term, you can check. It is exactly the same equation. So what we found in this way is that the manipulated equation in which we substituted lambda, analytical expression for lambda, is exactly the same as this guy multiplying the manipulated equation without constraints. Okay. So those two are equivalent, right? Somehow we can multiply manipulated equations without constraints by this operator. And what we get is exactly the same as if we expressed out lambda and got from it our manipulated equations without lambda, right? So we expressed lambda out, substituted back, and we got equations without lambda. Exact same can be achieved by simply multiplying manipulated equations without any lambda in the first place by this operator. And yeah. Okay. So this is what we managed to achieve. Let's now look at it a little bit more specific. So the dynamics can be rewritten this way.
Sorry,
right?
Professor, can I ask you a question?
Yeah, please. Yes, please.
Yeah, yes, and equation number 7.
Mhm.
Why it's equal to 0?
It is just the equation that I propose. Right. So this is not something that I derive. This is something that I propose. So the way logic works here is I say, okay, let's consider this equation. You know, any equation we can consider. We don't have to, we don't have to go to an oracle to get an equation. I can propose anything. And then what by simply manipulating this equation, so opening the brackets first, and then using this constraint equality here, I transferred by perfectly legitimate, manipulations. I get this equation into this form. So I prove that those two are exactly the same. But this allows me to prove that those two are exactly the same because, that is one of the same equation. So I transfer equation 7 into the form which is written as equation 9. But equation 9 is one and the same as equation 6. Equation 6, on the other hand, is a manipulated equation, which is in which we substituted analytical expressions for reaction forces. So with that, what I did is equation 7, which I simply proposed, became the new form of the manipulated equations with the reaction forces substituted. Do you get my logic?
Okay, thank you.
No problem. Any other questions about this whole thing? Okay. All right. Now, this then becomes expression for dynamics, right? So because is a perfectly legitimate equations for dynamics, just the reaction forces are expressed out. Where this guy, and it is actually this, right? Because remember, our sure complement here is actually analytical expression for it is J, H inverse, J transposed, all transposed, or all inverse. Okay, so all this becomes this expression. So the equation 10 then describes our dynamics. It's a perfectly legit way to describe our dynamics. So in terms of geometry, what it does is the following. So you have your dynamics, which is constrained. Constrained means that your generalized coordinates live on some manifold. Okay, there is some manifold, so some geometrical shape in generalized space in Rn, and on this surface live your constraint, your generalized coordinates. Generalized velocities in any particular instant live on a certain tangent space to this guy, right? Tangent space. And this tangent space is described as HQ dot. Oh, sorry, JQ dot. JQ dot, that's tangent space. JQ dot. Equal to 0. So it is in the null space of generalized of constraints Jacobian that generalized velocities live. All right. And your generalized accelerations live also on a linear space. It is also null space of the same Jacobian, but there is also a particular solution to it. So they live in the solution space of constraint equation differentiated twice, right? J q double dot plus J dot q dot. Now, in the space of solutions of this equation, leave your generalized accelerations. What this equation now does is it says, okay, here let me describe dynamics of the system. in such a way that without any reaction forces, we will still stay on this manifold. In particular, your accelerations instantaneously will always stay on their own linear subspace. Like for normal manipulated equations, generalized accelerations can take any direction, as long as it is achievable in terms of other components of the dynamics. They can always achieve them, right? Especially depends on the input. If input is full rank, so the input can be arbitrary Rn vector, then your accelerations will also be arbitrary Rn vector. Here is a different story. Here your accelerations will live on the subspace, right? On the subspace, on the space of solutions of constraint equation. And this dynamics here would perfectly describe it without the use of without the use of reaction forces. So without reaction forces, it would still stay on the manifold, right? Quite interesting. So this equation is, in a sense, implicit equation, whereas original equations that we discussed before. So, for example, let me go back to the first slide. This is explicit equation. Explicit because we have here explicit reaction forces, here explicit reaction Jacobian, and those are here explicit constraint equations, second order constraints equations, right? And those explicitly tell you manifold on which you will stay. Also, in this case, they tell you about the subspace of accelerations where they live, right? And they tell you how you're going to stay there, like because those reaction forces will enforce it, right? So that's explicit. Everything is shown. The same exact equation here, just manipulated a little bit, does all of this implicitly. So you don't know how it's done because it is all hidden inside this projector, right? But it is done nonetheless. So they still stay on the same exact manifold, but you don't see reaction forces and you don't see the manifold described anywhere. All right, so very economical description, right? Very compact, very few symbols, but does exactly the same amount of work. And whereas previously we have differential algebraic equations, where we have n differential equations and k constraint algebraic equations, right? Which even if they differentiate twice become also differential equations. So we have n plus k equations. Here we have n equations. So, less equations. Here, previously we have n plus k variables. So the number of variables, q is in Rn, right? And lambda is in Rk, right? So we have n plus k variables, n plus k equations. Now here we have n variables and n equations. So economical, not only in terms of symbols, but also in terms of variables and number of equations. Very nice. Sounds very good. Okay. This guy, I would propose to call it Schur projector. This is not from literature. That's just I use this term. At the end of the lecture, I will show you the references for the papers. There will be a group of authors who actually proposed all of this. I mean, I guess let's just look at them right now. I believe it will be slide 12. Right? Yeah, so these guys, Righetti, Buckley, Mistry, and Shah, they and like in some different configurations, like here, for example, another paper is by Mistry, Buckley, and Shah. That is not the only papers that they write. There is a body of like 5 or 6 papers at least. They established all of this. Although there are people who came even before them that did very similar work. And ultimately, all of this work dates to simple manipulations with Schur complement, right? So in a sense, it is these guys made it very explicit and very clear. But this, history of deriving this projector, as always in science, is quite long. Yeah, and I cannot put on myself to call it like a Rigetti projector or mystery projector or Shal projector. So I would like to. I would like if we could honor those people with their name in the projector. I just, I cannot presume to do it by myself. So that's why I should put sure projector to emphasize the role of sure complement that is essential when we derive an analytical solution. But hopefully later some people will decide to call it after scientists who popularized or derived this approach, right? Okay, so sure projector, this guy. You can see this guy, this projector, basically you can multiply your manipulate equations by this projector, and you get this economical description. Great, absolutely great. And this type of game, when you find something to multiply your original non-constrained equations, this game was played for a decade at least, and it was one of the kind of like directions in which this type of work has been done. Like a lot of work in terms of control design, in terms of simulations, and so on, was done specifically in this way. Like we rewrite dynamics in this economical form. Okay, well, this has been a direction in the field. Okay, so any questions about what we see here before I move on?
Yes, Professor.
Go
So
ahead.
here we have here projecting from Rn to manifold.
The projector is from Rn to Rn. But how should I put it? These equations will be I don't want to mislead you by answering simply. So they would be projected on a linear subspace, right? So instantaneously, not like as a differential equations, but instantaneously, this expression will be projected onto subspace in Rn, right? So while this projector, as the algebraic operator, goes from Rn to Rn, it is still a projector, so it cuts off some components, and it will effectively the vectors q hq double dot plus h small h would be kind of like squished into a subspace. Yeah, but this subspace is not the solution space of a constraint equation or anything like that. It is like a different subspace. But after we solve the equation, q double dot will be in the solution subspace. So this whole thing doesn't have to be in solution subspace. Only q double dot after you solve the equation have to be in solution subspace. And that is what this projector does. So essentially, what it does is transforms the equation in such a way that the solutions of this equation are correct in terms of constraints. Okay.
Good. Thank you.
No problem. Other questions? Okay. By the way, dimensions of this projector very easy to see because of this I here, right? Identity matrix. I is always square, so this guy is squared, so it projects from Rn to Rn. Cannot do anything else. All right. Now let us, before we continue, do a little bit of a remembering of linear algebra. Okay. It's just one slide. So for the equation, a affine equation or non-homogeneous equation, whichever you prefer, ax equal to b, where x is in Rn. Okay. Solution of this equation is a sum of a particular solution and null space solution. Okay. So it is the sum is of particular solution and null space solution. Now, particular solution is this A pseudo inverse B. Right? This is what we call particular solution. Null space solution I write in this form. Okay. So let me first discuss particular solutions, and I will explain why I wrote null space in this form. So particular solution, first of all, is a smallest norm solution. Okay, smallest norm solution. Why? Is by definition so, you can say. So you can say by definition, particular solution is the smallest norm solution. Geometrically, what you can think of solutions is something like this. There exists some linear subspace, okay, of all solutions, like all possible solutions are in this linear subspace, okay? And then there exists an origin somewhere. And from origin to this linear subspace, you can draw a perpendicular, okay? You draw a perpendicular, and this perpendicular will be stuck at the particular solution, like it intersects the solution space at what we call a particular solution, okay? And what you find is that by definition, perpendicular is perpendicular, right? Orthogonal. So this vector, let me draw it in, I guess, red. So this vector here, this red vector that looks from the origin to the solution, is orthogonal to all vectors that look from this solution to any other solution in this space. Okay. So if you draw the same, subspace here, exact clone of the solution space, but minus this red vector, minus particular solution. So if you subtract this particular solution from the solution space, what you get is a linear space, right? A linear space. And in this linear space, vectors will be always orthogonal to this red vector. And this linear space is null space solutions. They are usually either zero, there is either zero null space solutions, so only zero solutions, or there are infinitely many. You cannot have like 2 or 3, right? They always come in subspaces. They always orthogonal to the particular solution, and the particular solution is only one by definition again, because it is the shortest distance to the solution space, right? Right. So this is kind of like geometrical picture of this whole thing. Now, this is obtained by a particular solution is obtained by pseudo-inverse. Pseudo-inverse, by definition, is a procedure of how to find particular solutions. So, again, all of it is just like a definition stuff. Pseudo-inverse is a least squares procedure. You ask yourself, ax minus b, let's find a least error, like least residual, least norm solution. And you find that there is, pseudo-inverse provides you exactly that, like smallest error, smallest x solution. So both of those are independent. And what you find is that smallest x means zero null space, smallest error means particular solution. Okay, this kind of stuff. Okay, so this is a particular solution. It exists only one. By the way, it also lies in the row space of A. Row space, again, by definition, more or less, is a space of particular solutions to the equation AX equal to B. So all particular solutions to this type of equations constitute a row space of matrix A. Okay. Right. Now let's look at the null space solutions. So null space solutions, I wrote them in this form. Why did I do that? So what I'm trying to explain here is that null space solutions can be written as a projector. So you have x0, where x0 is arbitrary number. It's just any Rn number, okay? But we can project it into the null space of A. Okay, we project it into the null space of A. How do we do it? We use null space projector. This is a null space projector, and you can recognize that it is a null space projector if you studied a little bit of projectors. For example, this is clearly a row space projector, and I minus a projector gives you the orthogonal complement of this projector, right? So if this projects to the row space, I minus this will project to the subspace, which is orthogonal and, you know, to the original space, orthogonal complement to the original space. And for a row space, it is null space. Okay. So this whole thing you can recognize as a null space projector. Okay. Okay. Now, this null space projector, what it does, it takes any x you put in and puts it in the null space. And anything that is in the null space of A is a null space solution. Okay. But please remember that without particular solution, no solution exists. So you cannot just have this null space solution say it is a solution to the original equation. No, it is a solution to the homogeneous equation, right? So null space solutions are solutions to the equations Ax equal to 0, right? So that's what they're for, the Ax equal to 0. Okay. Okay. This form, the one downside is you can put infinitely many different x zeros that will produce exactly the same null space solution. So this is not a good way to parameterize the solution, because infinitely many x zeros will produce same null space solution, because this projector squishes dimensionality of the space, right? Rn is squished to null space dimensions. Okay. So like better way would be to find a basis in the null space and then use different variable to parameterize it, etc. But this form is very popular and very useful for various reasons. So this form of representing is very popular. Also, it is economical. You don't introduce more variables. All right. So again, there exists k-dimensional space of null space solutions, right? That's it, right? By the way, also just one last detail. This guy is a orthogonal projector. Orthogonal projector. Orthogonal projectors have various properties, which are very nice. They basically cut off every part of the vector which is not doesn't belong to the space to which we project, but they don't disturb the parts of the vector which already are in the space to which we project. And they have all kinds of very nice ways you could use those vectors. Right? Okay, but not all projectors are orthogonal projectors. Some projectors can do different things when projecting. Okay, okay. Now back to our dynamics. So this, if you remember, came from. Let me go back. This came from here, right? This expression, it has two components, right? This component related to right-hand side of manipulator equations, and it has this component related to right-hand side of constraints equations. Okay, two components. But the first one, we can decompose further into one component here, one component here. Okay. So yeah, if we are willing to do some manipulations, we could break this into three components ultimately. Okay. Now this here, but for now we have broken it only in two components. I think, yeah, two components. Okay. So again, these components, right-hand side of manipulator equations, this component, right-hand side of constraints equations. Okay. Let us look at it a little bit. So first of all, there is this quantity here, which is, if you look at it carefully, it is a solution to manipulate equations, right, without constraints. So if we had manipulate equations without constraints, we could write it out like this, and we can solve it like this, right? Interesting. Now, also, this quantity here is nothing but a weighted pseudo-inverse, okay, of J. So we have this constrained Jacobian J. Its weighted pseudo-inverse is this expression. And here, okay, we'll discuss this in just a second. So this quantity is a weighted pseudo-inverse of Jacobian constraints J. Notice it appears twice, right? It appears twice. Here's one appearance, here's another appearance. So this same Jacobian pseudo-inverse appears twice. Okay. All right, finally, this guy times this guy is like, here's them in a compact notation. They have to do with a particular solution to this equation, right? To the constraint equation. So just as this guy is a solution and only one solution exists to unconstrained manipulated dynamics, right? In the same way, here, what we're dealing with is some kind of a particular solution to this equation, except we use weighted pseudo-inverse instead of pseudo-inverse of this guy. Okay. So what I'm trying to say is that this whole thing makes sense, and we can rewrite it in this fashion. Let me show you. We can say q double dot is equal to 1 minus J pseudo-inverse J times A plus J pseudo-inverse times this guy. So notice what it looks like is exactly what we saw previously, right? Here is a particular solution. We recognize it by pseudo-inverse, but particular solution to the constraint equation. And there's a weight, right? It's a weighted pseudo-inverse, not pseudo-inverse. Here is what looks like a null space solution, right? Because it is like I minus J pseudo-inverse J. If this was a regular pseudo-inverse, it would have been just a null space solution. But here it's weighted. But instead of arbitrary vector, we have A, which comes from manipulator equations, right? So in terms of form, this is exactly the same as looking at the generic algebraic equation, but there is a detail, like what kind of pseudo-inverse we use, what are we solving, etc. So you could think of solution to the constraint manipulate equation as a particular null space solution. Particular solution comes from constraints themselves, and null space comes from dynamics of the manipulator. So dynamics provides you null space solution, whereas constraints provide you a particular solution. Right? Very, very interesting way of looking at it. Now, here is my proposal. This is, just to pause a little bit the lecture. Here, I claim that this is a weighted pseudo-inverse of J. Okay, with the weight being H, like H is a weight in this case. I guess yeah. Okay. So you can prove to me that this is the case. Like this is a weighted pseudo-inverse. When we say weighted pseudo-inverse, we can mean a variety of things, right? One way is to say weighted pseudo-inverse means it solves this problem. Minimize X transpose hx subject to, let's say, jx equal to, v. Let me use generic variables, okay? So we don't like x or double v x subject to ax equal to b. That is one way to write a weighted pseudo-inverse, right? It's a minimization problem, but minimization is a weight. Another one is to say that we want the residual of this equation with respect to v to be minimum, right? So residual of this equation has to be minimum, and x should be minimal, right? I've written as a plus, but those two should be somehow independent conditions, right? So this is another one, one of those which you could, which you could consider. Or you can just say, let's minimize it like this, right? Just minimize the residual with respect to omega. There are other ways to define what weighted pseudo-inverse means. Yeah, so important to keep in mind what exactly you meant when you defined it. So if you can prove that this equation is a weighted pseudo-inverse, and explain to me what you meant by weighted pseudo-inverse, you can just make like a small document or like Google Doc, anything like LaTeX, any ways that I can read and understand. You'll get extra points for that. The first like 2 or 3 people who provide original derivations, like not the same derivation, but if I can recognize your original thought, you'll get points. The way we do extra points in this course is like this. I will collect them as a sheet, and then at the end of the course, I will provide it to Anastasia. So we will add those points to the points for the labs and practical works. Remember, 50% of the points for the course are on the labs and practical works. So we'll add extra points there. But the cap will still be 50. So we're not going to exceed the cap. The reason is like for courses like this, where it is quite easy to earn points. Otherwise, everyone would get an A, or I would have to be very strict on the exam to keep the grades varied, right? I don't like automatic A's at the end. I like people to still prepare for the exam, so I apologize. For courses where it is very difficult to get points, extra points like more than 100 works. But for courses like ours, I'm afraid it won't work. But I'm very welcome towards your suggestions. If you think that somehow it would work, let me know. Explain to me your reasons. I would be very happy to modify the policy if your proposal is meaningful, better than mine, right? So anyway, for now, extra points would be maybe 5-10 points total through the semester. I don't know. We'll see. But yeah, for this task, if the first few who managed to solve it, I would generously give extra points. So this is a way to offset some problems if you like missed the lab, didn't get a perfect score on the lab, etc. This is the way, right? Just be active with small tasks like this. Okay. Sorry for interruptions in the middle of the lecture material. Any questions about that? If you have questions, we can also discuss at the end of the lecture. Okay. Good. So now I think I explained why this equation kind of makes sense, right? It has a structure. The structure is sensible. Good. Now let me present you with yet another attempt to write this problem in a compact way. So the attempt looks like this. Yeah, that looks like this. Here is again our manipulate equations. Okay. Again, our definition of what H is. So our constraint Jacobian, J transposed, can be used, rewritten using QR decomposition. QR decomposition. Okay. That is a new term that you haven't heard of before. QR decomposition provides you this type of expression. What is QR decomposition? Well, Q and R are two matrices that you get after QR decomposition. They have properties. Q is, as you can see here, orthogonal matrix. So it has properties of an orthogonal matrix, like a rotation matrix, you can say, right? Those types of properties, you have already seen them in SVD decomposition. Like in SVD decomposition, U and V on the sides, right, are orthogonal matrices, while the central matrix, sigma, is sigma is a diagonal matrix. Here, what you have is Q orthogonal matrix, and R is usually upper triangular matrix. But what is important for us is that Q is full rank. Q is full rank. Okay, so Q is full rank, and sorry, R is full rank. R is full rank. Right? Sometimes it is upper triangle, but for us, important enough that this full rank. And Q is a rotation matrix, like orthogonal matrix. Okay. Good. So we can decompose constraint Jacobian like this, and we get our equations in this form. HQ double dot plus small h equal to Q R times lambda. Notice we have some zeros here. That's because Jacobian, of course, is not full rank. Jacobian is full column rank Jacobian transposed, but not full rank. So it would have some zeros here, because otherwise it would be in full rank. Okay. Now, we can multiply this equation by this quantity Q transposed. What we'll get is manipulate equation here, multiply by Q transposed. And on the right here, there is nothing. Why there is nothing? Well, because Q multiplied by Q transposed is identity, right? Is one of the properties of orthogonal operators. So we get here identity, and you can see already this becomes much nicer looking because R is invertible. Okay, now we'll introduce what I would call switching variables. Those are very popular in, again, robotics literature. So you would see those introduced very often. So, get used to them. This idea of introducing switching variables is very typical for the literature. I define them like this. S1 is I and 0. Okay, so identity matrix and 0 blocks. And S2 is 0 and I. And this, I don't know if it is obvious, but this implies that if you stack them, so you write S1, S2, this will be equal to identity. Right? So if you stack them one under another, it will be equal to identity. Right? I guess if you want to be explicit about it, it will be like identity 0, 0 identity, but that is identity matrix, just a bigger dimensional identity matrix. Mm-hmm. All right. Now, if you multiply this equation by this switching variable, what happens is you get the switching variable here, and you get this, this equation here. So, right-hand side is exactly the same. left hand side, sorry. The right hand side changes though. Right hand side becomes like this. Why? Well, because when you multiply r with I, you get this r here, right? But when you multiply this 0 with 0, you get 0, and it is added, right? Because this multiplication goes like this, like r plus I times I plus 0 times 0. So this is just r here. So it's basically the switching variable. What it does, it cuts off a lower part of the matrix. It only leaves you with the upper part, right? Okay, nice. Now, when you do the same thing but with this matrix, what happens is this block is again preserved, like this block is again preserved here, right? The matrix, the switching matrix also appears on the left-hand side, but the right-hand side now is actually 0, right? It's 0. Why? Well, because when you multiply r by 0, you get 0. When you multiply 0 by I, you get again 0. So this matrix, it cuts off upper part, leaves the lower part of the matrix. But lower part in this case is 0. So all we get is 0. Okay. So we get thus two equations, which are exactly equivalent to the original equation. Because the original equation, we multiplied by identity matrix. Notice those two guys, when stacked together, are just identity. So in fact, what we did is actually, if we weren't such sophisticated people, we weren't in like advanced course, blah blah blah. What we could have said is this: let us cut this expression in half. Let us cut all the equations below that have zeros, and we get this guy. Let us cut all the expressions above that have r, and we get this guy, right? We just separate this in half. And that's exactly what those matrices do. They separate them in half. So we get the expression on top, and we get the expression on the bottom. All right. So this is what we did. Basically, very sophisticated technique, simply of cutting equations. System of equations in half, like not in half exactly, but like the way you like it. Zeros on the bottom, non-zeros on the top. Okay. Good. Now, the main advantage is that we can now compute like lambda if we want. We can compute q double dot if we want. Okay. We can compute lambda or q double dot. Okay. Okay. Now let us consider this bottom equation. Okay, this bottom equation S2 Q transpose, etc. Notice that this has exact same form as previously. Like we have something multiplying what is essentially is manipulate equations, right? Manipulate equations multiplied by something, and this something is a projector. So this is a projector. We call it QR projector. Okay, QR projector. This, to the best of my knowledge, is directly invented by those guys that I already previously mentioned, Shal and his various collaborators, like Mystery Rigetti, so on. So this is absolutely, as far as I know, everyone can make mistakes, so I'm sure I can too. But as far as I know, it is their direct invention, this projector, right? And you notice that they act very similar. So everything we said about the previous one can be said about this one, right? So I guess, except for the previous one, we could prove that because of the way we derived it, we could prove that it indeed describes original dynamics entirely, right? We didn't leave out anything. I guess we could prove that. Because what we did was just substitute into the equations. We didn't delete anything. here, since we use this C2 guy, we could actually delete something useful. So the technique is very similar, right? The technique is very similar. It gives you the same form, but it lacks the like one very important aspect, and that is the proof of equivalence. So that is a little bit of a problem if you're going to use it. In fact, I think you can provide counterexamples where this method will fail to produce here a equation which would adequately describe Q double dot. I think, but this is not in the literature, and claims like this you better make them with proofs, counterproofs, etc. So, but where it always works is for floating base dynamics of walking robots. So if you have a walking robot, the dynamics have this very specific form where this equation would always work. And that is what they prove in their paper. In fact, what they actually prove, and that is maybe what we will study next time, is that this projector leads to exact same results as this projector if you use it to solve inverse dynamics for walking robots. So it's a very strong result. It's analytic proof that you can interchangeably use those two projectors for inverse dynamics. But that is for walking robots. So I would would want to double check before I use it for arbitrary systems. Okay. Walking robots, one of the interesting aspects is that they, in a way, you can say that they don't behave like, they don't look like manipulators originally. They look like a floating body in the space with like appendages, like arms, legs, and so on, right? They look like floating bodies in the space. But as soon as the legs touch the ground, somehow they start to behave like manipulators. And this kind of like a relation, because of the degrees of freedom of the arms and legs, there is some kind of like very strong similarity. And I think part of it is being used here. Like, not everything that is developed for walking robots would be applicable to, for example, what do you call it? Closed chain manipulators, like parallel manipulators and so on. So you have to be careful a little bit. All right, sorry about that. It's digression. Yes. So you can see there are two ways to derive the same projector. Like you can have a projector derived using QR. You have a projector derived using Shure. One great advantage of a QR projector is that QR decomposition is actually fast. Like you can do it using SVD, and it is a rapid, easy to do thing. And actually, you don't have to do QR. As in, all you need is this type of this type of projection. Like it doesn't have to be upper triangular, for example, QR. It doesn't have to be. It can be anything that is invertible. So, whereas here, if you look at if you look at this guy, what is interesting is that it requires three inverses, right? One one inverse performed twice. You can store it in memory, so it's not a problem. But this matrix can be big, so inverse of this matrix is a little bit of a not optimal thing to do. And then you have this inverse of this bigger matrix. Of course, what you could say is that all of this is nothing else but a pseudo-inverse of weighted pseudo-inverse of this J transpose matrix. And this is then, if you can compute pseudo-inverse rapidly using SVD, for example, then everything is fine again. But the question remains open if if your software can do it. If you're going to do it by hand, like you're going to compute this inverse, then this inverse, you can run into trouble. So one of what the writers of this paper argued is that this QR pseudo-inverse projector is actually nice because it doesn't involve using H matrix. And I think in terms of practice, this does sound very reasonable. Computing this projector sounds much more appealing than computing the previous projector. So this is something to keep in mind. All right. Well, let me quickly see. Yes. So we don't have time, so I have to wrap up. But let me just give you a picture of where we are heading with this. So those two projectors, there are three, but the last third projector is, I think, just a variation on the first one. So I didn't want to put it here. Yeah, those two projectors are a way to write dynamics, constraint dynamics, in a way which is exactly the same as the non-constrained dynamics, right? And this is going to be a theme, like we will see it again and again. Here's just explicit discussion of how to do it, right? And after you've done it, there are various ways of how you could then proceed to generate control. There are ways to do it, like we would see next lecture, we'll see inverse dynamics based on this, and based on other ways to interact with those equations. So inverse dynamics used to be a huge topic in robotics of walking robots. It was something that people were solving. I think by now we can sort of agree that it is solved in a way, right? But yeah, so next time we'll look at those methods that people used, and we will I will stick to the most, I guess, practical, immediately useful, etc. I'm not going to do like a survey of the literature, so don't worry. And you'll see that this stuff is like those projectors are being used actively in those methods, but you don't have to use them. Like there are ways to do inverse dynamics without them, so this is also important. Yeah, and I guess what you have to look for here is just the fact that projecting dynamics is like in a way essential part of this whole process. In 3 lectures, we'll see a different type of projection. Like this projection here is, historically the first, I guess, way people were doing it, and is quite useful and quite obvious. Not in QR for sure, but this absolutely, like this is just a way to solve the equations. But later we'll see different type of projection, and it will be important to also differentiate between them. Okay. Now, I would recommend you, if you feel interested in the subject, I would recommend you to look at this paper in particular, because this one describes what I gave in the lecture. Sometimes in more details, sometimes it goes into inverse dynamics, which is the next lecture. Same here. This one is inverse dynamics ultimately, but they describe the same stuff that we did in the lecture. The reason I propose you to read it is because then you would see if you are already in a way able to read scientific papers on the subject. 2011 papers, to be sure, 12 years old, and for modern students this may sound old, but yeah, it's used to be cutting edge, and it's not like the field for inverse dynamics changed much since then. So this is like, we still use those approaches, so it's not outdated for sure. And you can see if you already have enough knowledge to understand this type of paper. So that's like, this would be a measuring stick for you if so far you gain any knowledge in the field. I propose you like try to read this paper, and if you feel like you can actually read it without comfortably, that already shows you that you got something out of the course. Okay, all right. That is it for today. Next time, inverse dynamics, and we'll slowly go towards control. But notice that this course is not going to be to end at control, because there's entire aspects of conductor controls that we didn't touch yet, like friction and so on. So we are moving towards control to then go to more advanced parts of what makes up controlling robots with contact. Right. Thank you guys for your time.
Thank you,
Thank you,
Professor.
Professor. Goodbye.
Bye.
Thank you, Professor.
Bye.